Alex. I am an associate professor at the University of Pennsylvania in the US, but right now I'm taking a sabbatical and I'm spending time at Microsoft Research under the AI for Science program in Amsterdam for the next year. And this is going to be a tutorial, or like a long tutorial, on neural operators in general. How many of you have heard or are familiar with neural operators as a keyword? Great, okay, some of you. So we're gonna go through the topic, and this is more or less the outline that I have prepared for these 6 lectures. So today we have 4 parts, and we'll focus on methods, on basically neural operator architectures. We're gonna go through the first 2 parts, describing some of the most popular ones, the deep nets that Matthias also introduced earlier, and the graph and Fourier neural operators. And then in the third and the fourth part, I'll try to revisit all those ideas from a dimension reduction point of view, and also from a computer vision point of view, and try to convince you that at the end of the day, maybe that's all what we're doing, and that kind of opens up a whole world of possibilities. For tomorrow, I haven't prepared anything. I'm just suggesting some topics, so maybe I can get some feedback today and see what would you be interested in. So the focus will be more on applications. I think in part 5, I'm inclined to go over generative models and uncertainty quantification. And then on part 6, it will be more on applications, how we can use neural operators to build fast surrogates for PDE solvers. Maybe we can talk about physics-informed approaches. We can talk about applications of all this to engineering design, through Bayesian optimization, handling complex geometries, and some more advanced topics. So I'll come back to this slide later on to solicit some feedback on what you would like to hear tomorrow. All right, so with that, I know it's 4 hours of me talking, which is not fun for me, so I hope I make it interactive. Feel free to interrupt me. Also, people online, just unmute your microphones and ask questions at any point, and let's get started. All right, so you're all super familiar with the explosive growth of deep learning over the last decade, or machine learning in general. So here I just want to point out that much of that progress has focused on building models that operate on data which reside on finite dimensional vector spaces. So for example, in computer vision, we're typically dealing with images, and images are represented as really huge vectors containing pixel values. So vectors that live in a very high dimensional but finite dimensional vector space. In language, we're dealing with words or sentences or text, and typically words are embedded into latent representations that we call tokens. And again, these are finite dimensional vectors. Similarly, in graphs, we have vectors associated with node or edge features. So for instance, if you're using a graph to represent a molecule, or if you're using a graph to represent a discretized version of a PDE solution on a mesh, again, on every node of that graph and edge, you will be representing, let's say, your velocity field, your temperature field, and interactions between the nodes using finite dimensional vectors. And we have great architectures to handle this type of data modalities, namely images, text, and graphs, convolutional networks, transformers these days. So there's a zoo of deep learning architectures and that are very successful in this setting. Now, taking a step back, and we are very interested in science and engineering applications for the most part. In many of such applications, we tend to model signals in the natural world as continuous functions. So here's an example in climate modeling or weather forecasting. We have continuous fields that you want to basically be able to query everywhere you want in space and time, right? At any spatial location and at any time instant. So these are continuous functions. They're not finite dimensional objects. They live in function spaces which are infinite dimensional. So part of the question that we're going to be asking in this tutorial is how can we build machine learning models or architectures that can naturally act upon and return representations of such functional data? And that might seem like an odd question to begin with, because now I just said these are infinite dimensional objects, so how are we going to grab them and stick them inside a computer? But we're going to see essentially how this works. So with that in mind, I'll just take a step back and try to walk you again step by step, starting from finite dimensional data, which I just mentioned. So for an example of that is in image classification, you have an input image, it's discretized on a grid. Now it can be represented as a vector living in R784, because that's the number of pixels you have in this binary image. And then for an MNIST digit classification task, we're asking a neural net to learn a function that maps from the input space R784 to the output space, which is R10, describing the 10 different classes, or the probabilities associated with each one of the 10 different classes. So this is a task of learning a function that maps between two high-dimensional vector spaces. Now, for many physical applications, we are presented with data that is defined as a function over some domain. So here's an example. You can think of trajectories of a dynamical system. These are functions of time. So the input domain is some time interval from 0 to capital T, and the output could be a state of your dynamical system, could be a vector that lives in D dimensions. But that's a continuous function because you can query that state at any point in time. Similarly, you have functions of space. This could be measurements over a continuous spatial domain, which is typically a subset of Rn. And again, you can define functions that you would want to query at any given point in space and return some outputs. So for instance, a velocity field or a pressure field or temperature. Even a single data point could be thought of as a function. Even in the finite dimensional case that you're dealing with vectors in Rn, you could still think of them as functions that map a set of integers, like the indices of the different components in the vector, to a real number. But more generally, and in this case, okay, you can, at the end of the day, you're dealing with a finite dimensional object. But if you're considering modeling the temperature field over the Earth, which is a function mapping from S2, basically the surface of the Earth, to the reals, then you cannot really uniquely identify every continuous function on the sphere by using finitely many numbers. So this kind of data is inherently infinite dimensional. It's a continuous function. So let's see how we can actually go about building machine learning models that can operate on functional data. Well, the first thing you can do, and that's probably something that everybody in this room has already done, if you come from an ML perspective or applied math background, well, okay, you're going to take your continuous function, you're going to discretize it on a mesh, let's say a uniform mesh, and now it looks like an image, for instance, if your domain is two-dimensional square. And now you can work with it, right? It's an image. You can feed it into your favorite neural network architecture, and you can predict what you want. So you're choosing to discretize first, and then take any of those successful ML architectures to work with. But now, what happens if you don't want to discretize first, and what are the pros and cons of making that decision of whether you should discretize or not? Well, the drawbacks of discretizing first are the following. If you choose to do so, the model that you end up building cannot really accept inputs at a different resolution. So if you have now an input at a different resolution, you will have to build a new model that can accept this input at this new resolution. So therefore, your model is inherently constrained by that initial choice. And what it ends up learning at the end is a function between the discretizations of the data you want, that you're working with, instead of the data itself. Similarly, if you would want now to make a prediction with that model at a new query point that does not, again, lie on the same grid, you would have to resort to some post-processing or some interpolation routine that takes place after you train your ML model. So the question that we're asking is, could we depart from that setting and kind of mitigate maybe some of those limitations by building architectures that instead of learning a function that maps between discretized signals, we can actually build architectures that parameterize operators that can map between continuous function spaces. All right? So much of this workshop will be on how do we design such architectures, what are the basic motivation and design principles, and how can we interpret them as dimension reduction tools or as computer vision tools, and then and then basically contrast and compare those different approaches. Now, what could we use this for if we were able to do so? Well, you can use it for multiple things. So here's some example applications. Let's say you're dealing with optimal control problems. You have a dynamical system governed by an ODE, and you would want to learn the map from any given control input function to the associated system trajectory. That is an operator mapping from a function g of x, which is the controller, to s of t, which is the trajectory of the system. Similarly, you could think of using it as a tool for building surrogates for PDE solvers. So maybe you have an input to the PDE that could be a forcing term or coefficients of the PDE or an initial condition, and you want to map that input to the full space-time solution of the PDE. So here I'll introduce the notation in a second, but u of x will denote general input functions, and s of y or s of t of y and y will denote output functions. And even more generally, you could think of using those tools to learn black box relationships between functions in general, regardless whether those functions are generated by PDE or something else. For instance, in climate modeling, or you may not perfectly know the PDE that governs the evolution of the climate, but you have snapshots, historical snapshots of how the climate has evolved in the past, and you could use those snapshots to try to learn a black box model for predicting the evolution of the system. All right. Now, as we will see, a lot of the things that I'm going to present, and basically pretty much everything that is out there in terms of machine learning models, is anchored on this hypothesis, the so-called manifold hypothesis. And this is the setting where we actually can do machine learning. So the manifold hypothesis states that collections of signals out in the world, let it be finite dimensional or functional signals, will actually tend to lie on low-dimensional latent spaces or latent manifolds that live inside their ambient function space. So if we have a collection of functions, U1 to UN, that live in some function space, let's say L2, in many of the problems of interest that we want to work with, there is some regularity structure. And then thanks to that regularity structure, those functions that we get to observe, they're not randomly spread inside L2, but they concentrate on a low-dimensional submanifold that lives inside of L2. And this is the goal of our ML approaches, to actually learn a good parameterization for that manifold. All right? So with that in mind, and I'll come back to that later, and there's a very nice paper that basically also illustrates that this is the context also for, in the case of parametric PDEs, namely that the solution of parametric PDE problems under relatively mild regularity conditions indeed concentrate on low-dimensional manifolds. With that in mind, we can formulate the supervised learning problem in a function space that looks very much similar to any supervised learning formulation you've seen before. Namely, that if you give me a data set that consists of n pairs of input and output functions, so input function U1 to UN and output functions S1 to Sn, then our goal is to learn an operator that maps between those two function spaces, such that this operator interpolates our training data as closely as possible, all right? With the hope that then we can also generalize to new test inputs that live within the same distribution of our training data, all right? So basically, we can interpolate the training data set. All right, so let's say how we can go about building such operator architectures, and we'll take two different perspectives, the DPONet and the FNO. They kind of have a slightly different motivation as a starting point. So we'll start with the first lecture on the DPONets, but before that, let me introduce a little bit of notation, so just to anchor the discussion. As I said earlier, we will be dealing with input and output functions. Input functions will be defined in a domain that I will denote as calligraphic X. You can think of X containing spatial coordinates, time coordinates, whatever are the arguments of your input function. And this calligraphic X will be a subset of RD typically. So we'll have functions U that are continuous functions defined on the input space X, and then those functions return outputs in RDU, okay? And I will denote as X as the input function location or the sensor location that we measure those input functions. Similarly, we have output functions. These functions are defined in some domain Y, again, could contain space or time coordinates, and they can return ds number of outputs, so u velocity, v velocity, pressure, vorticity, you name it. And then s of y will denote those output functions, and y is the query point or query location where we want to evaluate those target output functions. All right? Cool. So neural operators. I'll come back to this slide later, but this is just to say that all of the architectures that we're going to discuss can sort of be interpreted through this picture. There's going to be some encoding map that takes a continuous function and maps it to a finite dimensional latent space that I will denote by Rn. And by n, I will refer to as the latent dimension of my model, the reduced dimension. And then there will be a decoding map that takes a latent representation and then decodes it back to a continuous function that lives in the output space. And we'll try to construct architectures that follow this, mimic this encoder-decoder structure to approximate some general nonlinear operator calligraphic G. So we have a collection of input functions that is sampled from some measure mu. That could be our input functions in our training data set. And then we'll have measurements of output functions that are distributed according to the push-forward measure G of mu. And our goal is to approximate this operator G. So I'll come back to this picture later on, but this is just a schematic to keep in mind. So now let's see how the DeepONets do it. And we're going to travel it back in time in the 90s and go through the original work of Chen and Chen. So I call this slide a simple neural operator, and probably you're going to be mad at me because maybe there's nothing simple on this slide. So don't worry about the math here. This is just a statement that was proved in that paper. And it's a universality statement. Basically, the statement says that if I construct an operator that has this form, that is parameterized by some free parameters, some weights parameters, some bias parameters, and some type of activation function, if I use this specific parameterization for my operator, then Chen and Chen were able to prove that assuming that my model is big enough, they don't tell you how big the model has to be, but assuming that it's big enough, there exists some model parameterization that can bound your approximation error as much as you'd like. So that's a universality statement that any continuous operator can be approximated by a model that is parameterized in this way. It's not a very useful result, again, because it doesn't tell you how big the model needs to be. Just tell you some model exists, good luck finding it, all right? So now let's take a step back and see how this architecture is sort of motivated and break it down into pieces to understand maybe a little better how this formula looks like and what it does. All right, so this is what we'd like to do. We want to learn a continuous operator that maps from an input function space calligraphic U to some output function space. And we will assume that the input function space is compact. So essentially what we want to do, given an input function, we want to be able to evaluate G of U of Y. So G is the operator, acts on an input function U that returns some output function, and this output function is evaluated at a query point Y. All right, so this is the notation G of U of Y. So our goal is to approximate functions that live in the image space of that operator. So G of U is basically the set that you see here on the right-hand side of the slide. That's the image space of your operator. It's a function space. And my goal is to be able to approximate functions that live in that space. How should I do that? Well, a very simple way of doing that, since we have assumed that the input space is compact and G is continuous, that implies that the image of that operator is also compact. So the output function space is compact. And we know that in compact spaces, we can approximate elements of compact spaces by constructing a basis. So I would try to approximate every single function that lives in that output space by building a basis that can approximate it. So therefore, if you read the last statement, for every input function that is mapped through the operator, we will find some coordinates in this basis that we will use to approximate the target outputs. So this is the form of the representation. So any function that lives in the output space G of U will be approximated by a linear combination of basis functions, which are denoted by TK, evaluated at the query point that we wish, which is Y. And the coefficients of this basis are denoted as BK, and those coefficients will depend on the input function U. So a very simple linear representation of those target functions through a basis. And this is the Chen and Chen architecture that was developed in the early 90s. So basically now you can see, if you go back to the formula in the 2 slides ago, you will recognize that these coefficients can be expressed by this form. So you have some linear layer acting on the input function U with some coefficients xi, these are trainable parameters, some bias theta. You pass that through an activation function. You hit it with another set of coefficients Ci. That is a one hidden layer neural network that we will call the branch network. It takes an input function that is measured at M locations, M sensor points, so x1 to xm, and passes it through a one layer neural network to give you the coefficients Bk. So that is a branch network. And the second component there is the so-called trunk network that parameterizes essentially the basis. And instead of choosing a basis a priori, like Legendre polynomials, we're going to use, again, a one-layer neural network to parameterize those functions tau1 to tau n by this very simple expression that you see on the bottom left. Again, this is just a one-layer neural network. So weights hitting Y plus a bias, pass it through a nonlinearity. And that architecture is universal, according to the theorem of Chen and Chen. If you make it big enough, and by big enough, I mean here, if you set this number n to be large enough, so the number of basis functions you use to approximate your target outputs, If you make that number large enough, you have universality guarantees, all right, in theory. Okay, so that brings us to the DeepONet. Nothing changes. 20 years later, there's a Nature paper that uses exactly the Chen and Chen architecture, but instead of one layer neural nets, it uses deep neural nets. And that is a DeepONet, all right? And it enjoys the same universality properties as the Chen and Chen architecture. And again, this is a sketch. You have your input function. You're going to co-locate it at M sensor locations. You take that vector of M entries, you push it through a deep neural network. Let's call that the branch network. It will give you the coefficients, B1 to BP, let's say, of your bases. And then the second network is a trunk network. It receives as input the query point where you want to evaluate your target output functions. You pass it through a deep neural network. You get now the basis evaluated at Y. And then you just stitch those two things together with a dot product. That is your output of the DeepONet. Any questions? Yeah.
Initially, you said that these methods would allow us to learn with a single model from multiple resolutions, right? But is it possible to do that with this model? I mean, isn't the number of measurements all fixed?
Yeah. We'll get back to, yeah, so you're right. In what I'm showing in this slide, you're constrained, and your input function needs to be, basically every input function in your training and test data sets needs to be evaluated at this precise set of M fixed sensor locations. So that could be, you consider that as a drawback. We can revisit that and show later that, you know, you could use a different type of encoding an input function that does not have to rely on these fixed sensor locations. But for now, you're right. Yeah, that's sort of like a limitation of the DeepONet as you see it on the slide. Yeah. Y is the point, the location at which you want to evaluate your target output function. So we call it a query point, and we denote it by Y. Yeah. Sorry? Okay, let me go back through the notation again. So we have input functions U and target output functions, which either I call S or I can call them G of U, right? And those target output functions I want to evaluate at the query point Y. So this notation here denotes, so G is an operator, acts on an input function U, so this G of U will return some other function I can query anywhere I want, and then I choose to query it at location Y. All right? Does that make sense? It's a little bit of an overloaded notation, but that's what it is. All right, so that is the DeepONet architecture. It's basically a modern extension of the Chen and Chen theorem. Maybe encouraging for the students to see that you can publish a paper in Nature with a very simple sort of idea like this. All right, so let's revisit DeepONets. And again, in the back of my head, I will always be coming back in this dimension reduction perspective. So I'm just going to explain again DeepONets through this picture. You have, again, your input functions and your output functions. And the DeepONet basically follows this encoder-decoder structure that I mentioned earlier. So let me try to kind of demystify that. So again, we're trying to approximate an operator G through the composition of those three maps, an encoder, an approximator, and a decoder. So for instance, in the DeepONet, the encoder does the following. It takes a continuous function and just collocates it at M sensor locations. So it turns a continuous thing into a finite dimensional thing by evaluating the function at M locations. And then we end up with an M dimensional vector. That is one way of encoding an input function. A different way of encoding an input function is maybe to take that function and project it on M features or M basis functions. Maybe you can choose a priori a set of basis functions like Fourier basis or something else, and then project your input function along each one of those bases and take the projection coefficients as your kind of finite dimensional representation. That could be another way. Later on, we'll see in the Fourier neural operator, you can convolve your input function with the kernel, and then, so there's many different ways of designing encoders. But in the DeepONet case, it was just a very simple one. You just collocate the function at M measurement locations, or if you wish, you convolve a delta function with your input function. That's a different way of thinking about it. All right, so now the role of the approximator is basically your branch network. It takes an M-dimensional input and maps it into an N-dimensional, the coefficients of your bases. So there you could use MLPs, Or you could use convolutional nets. If your inputs are images, you can do all sort of things. Pick your favorite deep learning architecture, because this is where deep learning models live, right? They're helping you parameterize maps between high-dimensional vector spaces. Okay, and then finally, once we have now the coefficients of our bases in the DeepONet case that live in Rn, we would try to reconstruct continuous functions that we can query anywhere we want. That's the query point y, by constructing a linear combination of basis functions. So basically, the beta i's are the outputs of your branch net. These are the coefficients. And then the tau i's are going to be your trunk net, the basis functions. The empty argument here indicates that you can query them anywhere you want at any query point. And interestingly, depending on the choice you make for those tau i's, you get different models in the literature. So if you choose to parameterize those tau i's as MLP networks, you get the DeepONet that we just saw earlier. If you choose to parameterize these tau i's as trigonometric polynomials, you get something called the pseudospectral Fourier neural operator. That's another model in the literature. Or you could even use the principal component eigenfunctions. I'll come to that in a little later, but basically this is to say that depending on the choice of the basis you make, you end up with different methods. But finally, this is again a linear representation for reconstructing output functions. And if you think of this from a dimension reduction point of view, all this does is it learns a linear subspace in your output function space, right? And what is the dimension of that linear subspace? It's dimension n, all right? So basically, we are learning to represent output functions in this finite dimensional linear subspace that is spanned by these bases, okay? So it's a linear dimension reduction in function spaces, if you wish. Well, yes, of course, it could be, but we'll come back to that later, and also we'll try to motivate and justify why should we think about making it nonlinear. But for the time being, the DeepONet is linear, and this is what it does. All right? Other questions? All right, so now, thanks to the fact that this is a linear decoder, or linear way to reconstruct output functions, there is some interesting theory that one can do. And Chen did part of that theory, and later on, there was a paper by Sid Mishra in ETH that further developed that. The first theoretical result is, of course, the universal approximation result that I mentioned earlier, which is not so interesting or useful, as I said, because it doesn't really tell you in practice how you should choose the architecture size or what this latent dimension should be. But a more useful result in practice is looking into error, approximation error bounds. To do that, you have to make a few little assumptions, namely that the push forward measure, basically the distribution of your output functions has, it doesn't blow up. It sort of has finite second moments. And if you do that, you can study the covariance operator defined on the output function space. So basically, you study the covariance of your output functions. So the covariance operator is a trace class symmetric positive definite operator that admits a certain eigen decomposition. So this is a way, basically, of expressing the covariance operator through the eigenvalues and eigenfunctions of a kernel. So the phi j's are the eigenfunctions, the lambda j's are eigenvalues. And through the spectral properties of this covariance operator, we can actually quantify the convergence error that a model like the DeepONet will commit. And in fact, we can derive lower bounds for general models with linear decoders, including the DeepONet, that take the following form. So if you focus on the expression on the bottom left, this is a lower bound in the L2 norm that basically bounds the approximation error that your model will commit. And if you look at it, it's also, basically, this is the loss function we also use for training, right? It's an expectation. You draw input functions from the input measure. You push them through your operator. You record the outputs. You compare those outputs to the ground truth. And basically, that's an L2 error. And this error will be bounded from below by the sum of the eigenvalues that you end up neglecting, right? You remember, we kind of try to compress everything in an n-dimensional subspace. Therefore, we're neglecting all the eigenvalues from n+1 until infinity. and the sum of those eigenvalues will dictate the error. So no matter now what architecture you use, no matter how big your DPONet is, no matter what decoder you use, as long as it's a linear decoder, your model will be limited by this lower bound. What does that mean further? It means that if you're dealing with a problem for which the eigenvalue decay of the covariance operator in the output function space is fast, then obviously those higher eigenvalues will be very, very small, and it's safe to truncate and it's safe to neglect them, and you will get a very accurate model. On the other hand, if you're dealing with a problem where if you study now the eigenvalue decay of the covariance of the output functions, and that decay is very slow, then you will need a very large latent dimension n to capture this, and likely, your model will be super large, super hard to train, and things are not going to work. So that sort of indicates a very simple diagnostic that you can do before you train any DPONet or any operator learning model. Take the training functions, the functions that you have in your training set, the target output functions you have in your training set, and do a PCA over them and examine the eigenvalue decay. That will give you a hint of what should be the latent dimension you should choose if you were to build a model with a linear decoder. If that dimension is small, go ahead and use a DPONet, no problem. If this dimension is large, well, then probably you shouldn't use a model with a linear decoder. You shouldn't use a DPONet, and we can think about other solutions later on, going back to the nonlinear decoder case. So this is basically what this bound tells you in the L2 norm. You can derive a very similar bound in the uniform norm. And now what you see on the right-hand side is something called the Kolmogorov n-width. It's a quantity that people use to quantify how well can we approximate functions that live in the image space of the operator by using a linear subspace of dimension n. So for those of you familiar with model order reduction, that should be kind of a familiar quantity. But yeah, this is just another bound in a different norm. It doesn't, I don't think it changed the message that I just mentioned. You can read more about that in the references that I'm appending at the bottom of each slide. Okay. So I'm going to revisit this slide in the third part, where I will talk more about nonlinear decoders and give you examples for which, DPONets might fail because of this issue, because of the fact that the eigenvalues of the covariance in the output space decay very slowly. And you could imagine, again, if you have a model reduction background, that will be the case for advection-dominated problems if you're thinking about PDEs. All right. Now, let's see how we're doing with time. Okay, almost there. So let's see how we define the model, how we're going to train it. Let's see a little bit some of the practical aspects. So the training data set for a DPONet is basically a triplet. It contains input functions U, or basically the collocation of those input functions at M fixed locations. So you have input functions, as you see on the top left of the slide, and you evaluate them at M sensor locations that are fixed across your training and your test data sets. And then you take those measurements and then you stack them in a very long vector. That gives you, your measurements of the input functions U. Similarly, you have the query points at which you want to evaluate your target output functions. And then you have the target output function values in your training data set. All right? So this is how you would construct a training data set for building a DPONet. Input functions, associated query locations, and values of the output functions at those query locations. And once you have that in place, you just train the model by evaluating a simple mean square error loss, or a Gaussian log likelihood, just a standard training. You backpropagate gradients through that with automatic differentiation. It's a very simple implementation, and I can convince you of that. I have a notebook to share. Any questions? Yep.
Just to be sure I understood correctly, actually you have your model, which can be a PDE, okay? You choose a set of functions like, I don't know, sinusoids or polynomial, and you evaluate on a set of sensor points, and then you evaluate the PDE on the query point.
Yeah.
That's the...
Let me give you an example in the notebook, because basically I'm going to take a very simple elliptic PDE, like a Darcy equation, and then I'll try to learn a map from permeability fields to the solution of the PDE. All right? So let's see. If I get this right. And you can find those notebooks. There was another short course I gave with my students in 2022 at Johns Hopkins. So I can share the link in one of the slides, this Tripods Winter School. And I'm gonna walk you through the notebooks we had there for DeepONets and Fourier neural operators. So this is the DeepONet case. And it's a little bit of an outdated implementation, but I think it's enough to kind of take the main points across. So I'm not going to go through the methodology we just discussed. We can just go through the problem setup. So, this is like a standard toy PDE problem that you have a Darcy equation where U of X now is a permeability field, and S of X is your, let's say, a pressure field. And you want to learn the map from permeability to pressure, from U to S, for some fixed forcing function S. So you want to build a surrogate that if you give me any permeability, that surrogate can predict the full solution of the Darcy problem. So as a training data set, what you're going to do is to sample a bunch of U functions, a bunch of permeability fields. Here we do that by sampling a Gaussian random field to generate random realizations. I'm going to use then something like Phoenix to solve this problem with finite elements and get the ground truth solution. And now I have pairs, training pairs of input and output functions. So this is essentially the training data set for my DeepONet. I'm going to train on these pairs, and then I'm going to evaluate at test time at a new set of input permeability fields that I generated, but I did not use them for training. But they should also come from the same Gaussian random field. So you should stay within the right distribution, right? If I were to change the distribution which the test data generated from, those models don't really, you can't expect them to extrapolate. All right, is that clear? All right. Okay, so basically this is the setup, and I don't know how much time I should spend now because we have like 7 minutes, but I can sort of give you the main highlights. Here I'm using JAX because, in my lab we primarily use this framework for coding up deep learning models. So it's a very low level implementation, meaning that we implement everything from scratch. We're not using any existing packages and so forth. So here we have two neural networks. We have the branch network and the trunk network. In the trunk network, we use something also called Fourier feature encoding. So it's not so important, but basically allows you to approximate target output functions that might have higher frequencies. So because plain MLPs sometimes struggle with high frequencies. The loss function we're using is similar to what I said earlier, but actually we're using a relative loss. We're dividing by the norm of the output functions. That helps sometimes in cases where, let's say you have a bunch of output functions in your training data set, but then the magnitudes of different functions could be different. You have low magnitude or high magnitude functions. So if that is the case, using a loss that is not normalized will bias your model towards approximating functions with higher magnitudes. Because for those cases, the loss function will be larger, therefore the gradients will be larger. And those are the examples that will affect more the model parameters as you're training the model with gradient descent. So in order to remove that bias, you can normalize your loss in this form, or you could try to normalize your data before you train. So that's the trick with the relative loss. And basically, we just have those two neural networks, the branch network and the trunk network. And I'm not sure in this case, because we're dealing with 2D images, your branch network could be a convolutional network. And I'm not sure if we're using a convolutional net here or not. No, I think we're just using a plain MLP. Yeah, so basically that's kind of like the main function, the DeepONet. You have, your trunk network parameters, your branch network parameters. You apply the branch and the trunk network, and then you just stitch them together through a dot product. Here, everything is vectorized across all batch dimensions and so forth. So we're using a 9-sum operation to do everything in one shot. And then you compute your loss function, and basically that's it. Don't remember the details in terms of training set size. They should be mentioned somewhere, but I'm guessing we're using a couple of hundreds or a couple of thousands of examples. Oh, here, 1,000 examples. And the resolution is 100 by 100. And basically, once you train this model, you will see some statistics further down. Training takes like 2-3 minutes, and you get a relative L2 error on the test set in the order of 4%. Now, this is computed by taking all the input functions in your test set, push them through the network, you get a bunch of outputs, you compare those outputs with the ground truth, you compute the L2 error for each individual example, and then you average over those L2 errors to get a single number. So that's basically it. Maybe I can take some time. We have a few minutes for questions before we move on to the next lecture. 4 or 5 minutes.
Is there any recommendations where we can do the functions and then train it?
So in this case, for the input function set, you don't have a lot of flexibility. You commit to a set of M locations, M sensors. You should use M to be big enough that it captures the variability in your input functions. If your input functions is very smooth and nice, you can use a small number of sensors. If you have very high oscillations, you need a very fine grid to capture that, and things can become messy. For the output functions, there's no consideration there because you can evaluate those output functions anywhere you want. So wherever you get measurements, you can use them to train, and then you can also evaluate anywhere you want. So there's no issue there. Yeah?
Do you have the estimation of the covariance kernel and the decay of eigenvalues?
So in this case, it's super fast. That's why it works nicely.
And do you have it there?
I don't have it on this notebook, but yeah, I can show you other examples, maybe offline. But yes, back then, when we did this work, we had no clue those things are related, and we had no interpretation of this tool as a dimension reduction. So it was the early days of deponents. Yeah.
Can you go back to the slide that you talked about the covariance function?
Yep. It should be here.
The covariance function. So I looked up a bit lost. Sorry. What is the main? You were saying the universal approximation property gives us way less information than these other bounces. So what is the reason? What is the main differences between them?
So the universal approximation theorem is just an existence statement, right? It tells you there exists some model that if you make it big enough, you can approximate the target operator. But it doesn't tell you how big the error, for a given model size, what is the error you're committing. Whereas here, it sort of tells you that if you choose a latent dimension of your model to be n, the approximation error will be bounded by the sum of the eigenvalues that you're neglecting. And also, I should mention that this theorem also tells you what should be your optimal basis. So the eigenfunctions of this covariance operator should be your trunk network. You can never beat that. But now, question back to you. Why, in practice, why don't we just do that? Why do we need the trunk network instead of just using the eigenfunctions of the covariance operator? Why, though? I mean, it's just a PCA to compute them, but the answer is that in practical cases, you may not have sufficient measurements on those output functions. You may have very sparse measurements of those output functions, right? If you had high resolution measurements of your output functions, then you can do a PCA on those, and you can compute the eigenfunctions of the covariant, and that should be the optimal basis in the L2 sense for your, for your trunk. So you don't need the neural network for your trunk. So that's another point to be aware of.
That would be POD.
Yeah, POD, PCA, yeah, we can, same thing.
Yeah, no, sorry.
Yeah. And you can still have the branch network to learn the coefficients because that allows you then to generalize to new input functions. Other questions? Okay, so I guess, yeah, the take-home message is basically, for me at least, is sort of, is this slide that, I like to view DeepONets as a linear dimension reduction tool. Basically, can learn a linear subspace for representing your target output functions. Okay, so we are exactly at 2:45, so I'm gonna move on to part 2. All right, time flies. So part 1 is done. Part 2 comes up. And now we're gonna take a step back and we're gonna revisit this whole operator approximation game from a different viewpoint that has nothing to do with the linear subspaces anymore, but is more kind of deep learning motivated and kind of neural network motivated. So we're going to talk about graph and Fourier neural operators. Again, this is the outline of everything. And yeah, so placeholder.com does not exist there. I should remove that because I have not uploaded my slides and code anywhere. I was planning to, but all right. So let's see an alternative architecture, a different way of approaching the problem and building a neural operator architecture. And this approach is going to be motivated by standard neural networks that we know and we love for finite dimensional regression. And this is what a standard neural network does, right? It's designed based on two simple operations. Linear transformation, so take your inputs, hit them with the weight matrix. So that's a linear transformation, followed by nonlinearity, and then repeat that fundamental building block many times to make the architecture deep, right? That's what an MLP does. And of course, we have all the approximation theorems and blah, blah, for MLPs that for under appropriate choice of the activation function and enough width and depth. Again, this is an existence result, not very useful in practice, but we have this guarantee that we can approximate any continuous map between finite dimensional vector spaces. So can we take kind of this motivation, this picture, and try to find ways to generalize it to the function space setting so we can build neural operator architectures? So that's basically what the graph and the FNO architectures do. And the main point to observe here is that once we take this leap from finite dimensional spaces to infinite dimensional spaces, now we have a richer class of transformations, linear transformations that one can play with. Whereas in MLPs, this is just a point-wise linear transformation. You just take a vector as an input and you hit it point-wise with a matrix. Once now we kind of abstract things and we move to function spaces that are infinite dimensional, we can define linear operators that are not acting point-wise on the inputs. And an example of such operators is this kernel integral operators that basically take the following form. So on a continuous function space, you can pick a kernel function, a continuous kernel function, and you can build linear operators that act on inputs of this function space through this form. So basically by convolving the input function with a kernel, basically integrating out the second argument of the kernel, that returns another queryable function, right? So the empty argument here is the query point. So that's a valid linear operator. And why don't we use something like that as a building block for an architecture? There's some further motivation of why one could use this type of kernel integral transforms, and that comes from the theory of elliptic differential equations, because we know that solution operators to such equations, so if you have an equation, linear equation in the form LU equals F, where L is a linear differential operator, of course you want to solve this equation, you want to learn the inverse of the operator L, so that if you give me a new forcing term, I can instantly predict the solution U. And we know from the theory of linear elliptic equations that the inverse operator is very intimately related with the kernel integral transform, where we're integrating the force function against the Green's functions kernel. Okay, so that's another extra motivation of why should we be looking into this type of linear kernel integral transforms. So this is the main idea behind graph neural operators. So now, instead of having just point-wise transformations, so this is your classical MLP setting that you take your input function, evaluate it at some query point, and you hit it with a point-wise linear transformation. In addition to that, I'm going to add another part that is inspired by this linear transformation, this kernel integral transform. And there's an interesting sort of, another interesting thing to observe is that the second part of this transformation contains global information about your input function, right? You take your input function and you're integrating it across the entire domain. So this part carries global information about your input function, whereas this term carries local information about your input function evaluated at a specific query point Y. So I'm going to build a layer that has two linear transformations, a global one and a local one. I'm just going to add them together, hit the output with a nonlinearity, and make that architecture deep. So that's kind of the approach of a graph neural operator. All right? So take the same sort of motivation and notion of MLPs, but try to extend it in function spaces by also augmenting your representation with this type of global linear transformation. All right? And the cool thing about this architecture, the first cool thing, is that you're no longer restricted to a fixed number of input function measurement locations. Because for any measurement location, you can always integrate it against the kernel, right? So basically, the measurement location becomes a query argument. So you could have measurement locations in anywhere you want. This is the Z. And then you're just going to integrate that against the kernel, evaluate at Y, and that's a valid representation. You're not limited to where your measurements live. You're essentially discretization invariant in this case. All right? Any questions about the motivation? And so this is a basic neural operator layer, if you wish. Now, the name of the game is how do you compute this integral in practice? Because that's the only difficulty, right? How are you going to go about? This part is trivial. You just evaluate your input function, hit it with a trainable weight matrix, no problem. This part, you need to do a little bit of work to approximate it. So we're going to see now how this is done. Option number one, well, okay, Monte Carlo. So we're going to approximate the integral by evaluating our input function at a finite number of locations, of measurement locations. Let's call them Zi from I to N. And typically, if your input function has nice structure and kind of is regular, this kernel may typically rapidly decay off its diagonal, meaning that in order to evaluate this integral, you can just focus on doing Monte Carlo in a small neighborhood around your evaluation point. Because further away from this neighborhood, all those correlations die and the kernel tapers off, and there's no contribution to this integral. So basically, the graph neural operator takes the approach that, okay, for any given measurement or query point, we're going to construct a local graph in its neighborhood. And based on the function values in this neighborhood, we're going to do a Monte Carlo approximation of the target integral. And essentially, this results into a graph neural network that you can basically map directly into a message passing algorithm on a graph neural network. So this is a graph neural network. And the more rounds of message passing you do, or the more deep you make this architecture, the more local information propagates kind of outwards from each node and becomes global information. And there's additional computational tricks for making this more efficient using low rank approximations, Nystrom approximations, multiple versions, and so forth. But the main idea is this Monte Carlo approximation of the integral, all right? In a local neighborhood around each evaluation point. But nobody uses that anymore. So everybody's using the option 2, which is the Fourier neural operator. And this is just basically a more convenient, computationally convenient and faster way of approximating this kernel integral transform. Specifically, we're going to make the assumption that we're going to use now stationary kernels alone. Basically, kernels that are translation invariant. They only depend on the distance between the two arguments. And by using stationary kernels, that allows us to approximate this integral in the frequency domain. And instead of paying quadratic cost in the number of points, now we can pay n log n cost in the number of evaluation points, because you're going to take your input function, evaluate it on a regular grid, do an FFT, and now this convolution becomes a multiplication in the frequency domain. So basically, you take your input function, U hat is the FFT coefficients of the input function, which we will typically truncate on a finite number of modes. I'll come back to this truncation a little later. Now we're going to hit this with a trainable weight matrix. This is K hat, multiplication in frequency domain, and then inverse Fourier transform to map back. So that's a very fast, computationally convenient and fast way to compute this kernel integral transform. All right? So that's really the idea here. And there's benefits to doing that, of course. As I mentioned, the graph neural operator will come with quadratic cost in the number of measurement points. And the other cool part is in the graph neural operator, you have to refine the graph to make predictions at higher resolutions. And then the cost will increase because n is the number of nodes in the graph and the cost increases quadratically. Whereas in this case, you can really easily go from coarser to higher resolution without really having to rebuild a neighborhood graph, as long as you restrict yourself on regular grids so that you can use the FFT. All right? Yeah, and naturally handles non-local transformations, because now the whole integral, which is a global operation, is computed in one shot. You don't need to construct local neighborhoods and then kind of sort of truncate things to a local neighborhood around the point. You're using the full global information from the input. Any questions on the FNO architecture? Is that more or less clear? Yeah. Okay. All right, so this is a graph of how it looks like. So this is a Fourier neural operator layer. And again, we have these two components, a local conditioning. So you have an input function U, you evaluate it at your target query points. So Y, again, is the target point that we want to evaluate the output function. We can also evaluate the input function there. W is a trainable matrix. So this is the local part. And this is the global part, which is an FFT approximation of the kernel integral transform. So you take your input function, evaluate it globally on a regular grid, do an FFT, take the Fourier coefficients, hit them with a trainable matrix. Now you have a trainable matrix for the real part and the imaginary part of your coefficients. And then take the output of this inverse Fourier transform, and that's the kind of the non-local part. You sum them up, kind of like looks like a residual connection visually, the summation. Stick everything through a nonlinearity, and that's a single FNO layer. Now you can start stacking layers to your FNO similarly to what you do in MLPs. All right, and you make the architecture deep. And it works amazingly well for problems that generally have smooth structure, like the target functions have smooth variation in space and time. It doesn't work so well with functions that have discontinuities. And it doesn't play that well also with data that could be corrupted by noise, because then FFT breaks. It's not a very robust transformation with respect to noise perturbations in your inputs. Sorry? Yeah, you can do some filtering, pre-processing to try to remove noise. Or you try to use different types of transforms like wavelets or something that might be a little bit more robust to something called a scattering transform, which is a wavelet-based. Yeah, but that, things get a little more complicated on the implementation side. All right. And okay, we have universality results, those type of interesting but not very useful results. Again, make it big enough and you can approximate any kind of operator. And maybe before I go to training, going back to that original image that I had in the very beginning, encoder, decoder, it's not so clear now how you can view the FNO as a dimension reduction tool, right? Maybe going back to this picture, yeah, it's not entirely clear how this fits into the dimension reduction viewpoint, but the interesting part here is because we are composing layers of this architecture and we have activation functions, ultimately, this technique can learn nonlinear manifolds in the ambient function space, unlike the DeepONet that is by construction limited to learning linear subspaces. This architecture has the ability of picking up nonlinear manifolds. And it's kind of interesting because for every input function, you have this part here that kind of, this part is linear, so that defines a linear subspace that is anchored on your input function, and plus some nonlinear part that comes from the global conditioning. So yeah, it's kind of hard for me to interpret this as a dimension reduction tool, but you may think of this constructing a linear subspace that is, for every example in your data set, this is constructing a linear subspace that is anchored to that input example. But then by stacking layers, you're kind of warping that space and making it nonlinear. So it's kind of, that would be my closest interpretation of what's going on from a manifold dimension reduction point of view. So yeah, it's a more powerful architecture than the DeepONet, but a little bit more fragile when it comes to irregular functions or noise. Okay, so that could be a great baseline if you're doing operator learning and you want to compete or compare against a strong baseline, a good model. That could be a good choice, again, for the examples that it doesn't break. All right, and then the training is relatively straightforward. The only requirement here is you have to constrain yourself to regular grids, okay? So in 1D or 2D images and so forth. There are some variations of the FNO to handle more complex geometries. Yeah, but the vanilla version, you have to stick to regular grids. So a single training example is basically the locations where the input functions are evaluated with indices on a regular grid, the corresponding input function values, the query points, and the corresponding output function values at those query points. So that is the FNO. And actually, I was pretty fast going through it, so maybe we can take more time and see the notebook. Or maybe I can take questions about the methods before we see the computing part. Are there any questions on the motivation or yeah?
No, just a question on the R curve, that diagram here.
Yeah. Yeah, maybe I can explain this diagram a little better. So V of x is the input function, or U of x. The bottom part of the diagram is this simple element-wise, point-wise operation where a trainable weight matrix hits the input function evaluated at the query point y. The top part of the diagram is the part that uses the Fourier transform to approximate the kernel integral transform. So basically, you're performing a Fourier transform that acts globally on the input function. You get a bunch of Fourier coefficients. So this is this R part. And what happens also here is that you're going to truncate your Fourier coefficients. So this is why you see many modes here, but less modes here, is because a truncation takes place.
We are shifting the numbers.
Yeah, the shifting, I don't think that's so important. Is mainly the truncation part that happens there. And that is a hyperparameter that the user has to choose. So for instance, if my input signal is one-dimensional and is evaluated on 100 grid points, equispaced, if I do an FFT, I will end up with, is it 100 Fourier coefficients or 200? I'm not entirely sure, but then there's a hyperparameter the user has to choose that to truncate the Fourier spectrum. So you're going to keep the leading, let's say, M Fourier modes. And that is sort of like a blessing and a curse, right? On one hand, by doing that, you're adding some inductive bias to your model, because by keeping only the M largest Fourier modes, you're kind of truncating anything that is noise or high frequency. So basically, you're biasing your model to approximate smooth things. But at the same time, it's a curse, because if indeed your target outputs are not very smooth and have very high frequencies, you're kind of like throwing away information by doing that. But it's also done for computational considerations. By doing this truncation, you have a smaller number of trainable parameters, and the operations are also cheaper to perform. But it's a key part in FNOs, the number of modes you choose to use in the FNO layer is an important hyperparameter. Other questions? Yeah.
Question just to be understand. You said that also somewhere in this VMO part, we're actually using a weight matrix to weight VMOs.
Yeah.
But would that happen so after the truncation?
That happens after the truncation, correct? Yeah. Yeah. Because it would happen before the truncation, the weight matrix would have to be a lot larger. Yeah. Yeah, so basically you will end up with a much larger layer. So the weight matrix that hits that will be a lot larger. You could do that, but then you're just going to end up with a really large model very quickly. As you start composing layers, it will become huge. It might be harder to train. Yeah.
Sorry, just one question. The kernel is the thing that you have learned here, right?
You're learning, yeah.
Matrix and the kernel.
So this one and the K-hats, yeah.
No, okay. And V is a scalar. Y is a matrix because they will evaluate V at multiple points.
If V is a scalar, then W is just a scalar as well. But V could be like it could be a vector. Yeah. You could have multiple channels in your inputs, and then W becomes a matrix.
Sorry, last question. So the fact that the kernel has to be shifting variant does it limit the middle somewhat? No, because it's a universal approximation problem.
Yeah, it doesn't limit the method, and of course, again, you also this architecture, I think, gains its expressivity by stacking multiple layers. I'll come back to this a little later, but a single FNO layer, well, we'll see that in part 4. You can interpret this as an MLP. I'll show you the structure. It's an extremely simple building block. It doesn't have a lot of expressive capacity. But by stacking multiple layers of that on top of each other, that's where it gains its approximation capability. Yes.
How do you deal with the complex numbers of the Fourier transform?
So you can split it into real and imaginary parts, and then it may become real numbers, right? You have to be a little careful how you do gradient descent over that. I'll show you in a bit in the tutorial. You can just rewrite the Adam optimizer to act on complex numbers. It's not that hard, yeah. Yeah, or on a validation loss, yeah. Cross validation. Other questions?
Number of the can you make how to identify
No, it's just a hyperparameter that you have to set a priori for all layers. Yeah. I think you could use different from layer to layer, but that's again a hyperparameter that needs to be chosen for each layer. Later on, when I'll show you the neural network interpretation of what is going on here, you will see that you could do more with this. I mean, nobody has really done that, and we've tried playing around, and it didn't really, work that great. But you could think of randomizing the selection of frequencies. You can think of playing a lot of different games here. Of course, in this case, you're not going to be using an inverse FFT. You'll have to do things manually in terms of how you invert. But yeah, there's some flexibility, but the original version that tends to work quite robustly is what you see here. Yeah. What do you mean by that? Well, then this X here will also contain time coordinates, and that should not be lost, right? That information should still be there. If you consider time-dependent inputs, then you're acting on the time axis as well. But it really depends on the problem setting, right? So in PDEs, there is different classes of tasks that people use this type of neural operators for. So for instance, you can learn a map between coefficients to the solution, or you could try to learn an evolution operator. If you're giving the PDE state at time t, I want to predict at t plus delta t, right? So now you're kind of discretized in time, and you're doing kind of like next time step prediction. So the operator learns how to map the current state to the next. In that way, it does not receive time as an input, right? You give it a special field, and it predicts the next special field. Yeah.
So in this line, if you have multiple inputs, and one is very, let's say, fine scale features, and the other very low. So basically, time would be very, let's say, active in time, dynamic in time, then in space, very flat. If you put it all in the same neural operator, can you distinguish? Or otherwise, can you split the neural operators for high and low frequency components?
Yeah, I think then you see that's the time, for a given problem, you can start customizing things depending on the problem nature and structure. You can concatenate time as an additional, well, we have to think of a specific example to give you. I don't have a general answer to that. Deponents. Okay, 1 second. Actually, would that help if I show it here, like this sketch? This one? Oh, the encoder decoder. Yeah. Sorry, 1 second. This one. No. Yeah. Yeah.
So you don't use the machine learning.
Yes, you could do that. So for instance, maybe I can try to come up with an architecture. You cannot see the slide very clearly, right? Or why is that? Sorry, one second. I'm not sure why the slides are all messed up now. Hopefully this will. Okay.
My question is that the compare the model as a reduction. But here I see no, here I see evidence on learning in model reduction.
Mm-hmm.
It's just the linear approximator.
Yes, I mean, there's many choices one can make, right? So let's start with the choice that is more closely related to dimension reduction. You have two sets of functions. You have input functions and output functions. One thing you could do is you can take all your input functions, run a PCA, and that can be your encoder. You can take the projection coefficients to those eigenfunctions to be your finite dimensional representation of that data set. Then you can take your output functions, do the same, and now you have a finite dimensional representation of your output functions. So then the only machine learning component now will be this approximator map that will learn to map between those two finite dimensional spaces. So that's a valid model. I think it's called something. I mean, there's a paper about it from the same group at Caltech that is PCA based. All right, so you do two PCAs, one on your input space, one on your output space, and then you have some neural network that learns how to map one space to the other. So that's a valid model. The DeepONet doesn't do that. The DeepONet actually has a different choice for an encoder. It just takes point-wise measurements of the function, and then the approximator is just an MLP. And also the decoder has a bunch of MLPs because we're learning these basis functions. Instead of using the eigenfunctions of the PCA part, we're actually training an MLP to learn a basis. So that would be the DeepONet. Does it make sense? Now, maybe an argument of why do that versus do the two separate PCAs in the beginning is that when I go ahead and I do a PCA, let's say on my input functions, I'm going to learn a set of features that compresses my input data set, right? But really my goal here is to predict the output function. So those set of features I'm learning by doing a separate PCA on the input set, they're not necessarily useful features or predictive features for the task I want to accomplish, right? Which is predicting the output functions. And that's maybe one argument for not doing that. And instead doing kind of like an end-to-end model that, does everything kind of in a connected way, like the DeepONet does, for instance. But yeah, there's a lot of flexibility. Like if you see things from this viewpoint, we can, spend the whole weekend coming up with different models that fit this picture. And in part 4, I'm going to open the picture to the computer vision side of things, which we could sit down for a month and come up with different models. So, yeah.
Imagine that you already trained this.
Yeah.
So you have some predictions of your output. And you are allowed to add a few more samples for learning.
Mm-hmm.
How would you sample?
How do you select? How do you add? How do you do acquisition of new data in a smart way? Okay, that we can talk about tomorrow, because for that you need some also notion of uncertainty quantification to guide that selection process. So as you're talking about active learning now, that, okay, I start with an initial data set, I train a model, and then I'm asking the question, if I have the budget to collect some more observations, which are the most informative ones for improving this model? So for that, you need to have an access to a notion of not just what your model predicts, but uncertainty around that prediction, and use that uncertainty to derive a policy for acquiring new data. So similar to active learning, or an optimization content is sort of Bayesian optimization. But the uncertainty quantification plays a role there. Yeah, I think.
Like, for example, you want to know which input field leads to some extreme values of your outputs.
Yeah, I mean, you can compute sensitivities in the sense that Yeah, I mean, you can compute sensitivities, right? Everything's differentiable here. For whatever input, I can compute gradients through the whole network and give me sensitivities of the outputs. But that reflects the sensitivities of that neural network, right? Not necessarily the actual system you're modeling. So I'm not sure to what extent that is super useful. I'd be more interested to know in which parts of the space my neural network is most uncertain, and then go gather more information there to improve the neural network itself. And you can bias that search towards regions that also lead to extreme outputs, for instance. That goes all into the design of that policy for how you're going to acquire new information. So you can put more emphasis on not just exploring anywhere in the space where the uncertainty is large, but also prioritize regions that lead to extreme outputs. Yep.
The graph neural network with the imperial operator design. To me, can it be used to learn also boundary conditions, for example, for magnetic field, we have this open boundary problem. Is it possible to learn also the boundary conditions with this green operator?
I mean, you would, I'm not.
With another branch, another.
So I'm not so familiar with the problem that you're describing, so I wouldn't know. But if you can pose the problem as a learning problem from one function space to another, you could use this architecture to parameterize an operator. Other questions? Good questions, by the way. Okay, slides are slowly getting a bit more clear, but now I'll try to switch to code. So this is the FNO notebook. The implementation is also relatively straightforward. Same kind of benchmark here at Darcyflow. There's two little tricks. As someone correctly mentioned earlier, we have to deal now with the matrix that hits the Fourier modes in the frequency domain, because now the coefficients are complex. We're hitting it with a complex matrix, which you can also split into two matrices, one acting on the real part, the other one acting on the imaginary part. So these are basically the two implementation choices. Either you split it into two channels, real and imaginary, and then nothing changes, or you actually you cast it as a complex number, and you use complex entries in your weight matrix, but then you have to change the optimizer so that it can do parameter updates in the for complex numbers. So both of them are valid. Here we kind of took the more adventurous route to use complex numbers as parameters and then tweak the Adam optimizer so that it can perform gradient descent updates on complex variables, which is now no big deal. You just have to be careful with the only thing that changes in the implementation of Adam is this line here, where basically you have to compute the conjugates of your complex of a complex number. So nothing too scary. It's just a one-line modification to an Adam optimizer implementation. Okay, so this is sort of how the model is going to look like in the FNO case. So you have you're stacking a bunch of layers. I wouldn't argue that this is the best implementation or the fastest, or could be a little bit awkward as well, because we have to do this permutation of the indices and the channels. But the bottom line here is that we're just going to stack a bunch of Fourier blocks. You see that the hyperparameters here is this number of modes. This is the number of modes we'll use for truncation, followed by some activation function, and then finally a linear layer and returning predictions. So this is really kind of the meat of the implementation. This is the kind of the apply function, the forward pass of the FNO. So basically you have the trainable parameters for the Fourier layer. So this is what I call a spectral convolution 2D. So this routine here computes the kernel integral transform part. So you have your trainable parameters. You're going to do an FFT, a forward FFT on your inputs, and then you have to This index update function, this complex multiplication to d is defined up here, is basically multiplying the Fourier coefficients with the trainable weight matrix. And because now we're dealing with a real input signal, there are some interesting symmetries in the frequency domain. So in fact, you don't need to account for everything. So this is why you see here this kind of weird indices in the arrays, because we don't need to operate on all the frequencies. There's some symmetries, and we can reduce the amount of computation that needs to be done, and the size also of the weight matrices that need to be done. And then finally, once you're done multiplying the relevant Fourier modes, you do an inverse FFT to map things back to the physical space, and that gives you the kernel integral part. Let's say now if you want to extend this in 1D or 2D, you would have to modify this piece of the code and to implement the spectral convolution for 1D signals or 3D signals. But it's pretty straightforward. And this is the FNO block, which now once you have the spectral convolution in place, you have the convolutional part, you have the local part that you just hit the input function with a dense layer, and then you add those things up. The loss function is again the relative L2 loss, and similarly to before, you just basically train. And as you will see, this model does a little better for this example. Also super fast to train. It takes 3 minutes on, I think that was just on Google Colab, or maybe some GPU we have back at the university. And you get a relative L2 error on the test data set in the order of 1%. DeepONet was around 4%, if I remember from the previous notebook. So yeah, I'm going through this fast, but you can obviously, this is something you have to take time to study at home and maybe try to do it yourself. That's the only way to figure out what's going on. So we actually have a lot of time for questions, which I can take, or I can move on. And yeah.
So I noticed that in the Fourier neural operator layers, you always just use standard Fourier transforms.
Yep.
Which in some sense always assume like the periodicity of your signal. Right?
Correct. Yeah.
And so is that by design, or is it just that happen to be transformation?
It has to be the case because you're using an FFT. If you're not dealing with periodic signals, you can do padding, basically. So you can extend the domain by padding and just add a bunch of zeros, like do a periodic extension of your domains, right? Any signal that is not periodic, you can think of extending the domain to making it look periodic, and then apply FFT there. So that is a trick that is employed in practice when you're dealing with non-periodic inputs. That's a good point. Yep.
So is it also possible to write a DeepONet in a physics-based loss function without data?
Yeah, well, that's what we call a physics-informed DeepONet. Should we talk about that since we have time? There's also physics-informed neural operator, Fourier neural operator. Okay, so maybe I can jump to that. I have some slides somewhere. Let me see. I think in part 3 I had some slides on that. Yeah. Okay, maybe this is a good starting point. Also, there is people online. I haven't got any questions from there. So, yeah, are there any questions from the audience online before we move on to something different? All right. Well, feel free to just jump in. Okay, so let me motivate the physics-informed part from the neural PDE surrogates point of view. So we want to potentially use these deep learning tools as dimension reduction or reduced order modeling approaches to build surrogates for PDE solvers, right? But now there's sort of like a chicken and an egg problem. Like we want to replace the PDE solver because it's too expensive and use a surrogate. But before we're able to do that, we need to call the PDE solver maybe 10,000 times or 1,000 times to generate a training data set for that surrogate. And it's okay to do that for all the toy examples you see in the papers, but it's not okay to do that for large scale, serious PDE solving. So what do we do? Is there anything we can do in this setting? And so there's a need for data efficiency, basically. Is there a way we can train those neural operators with either small training amounts of labeled examples or even the extreme limit of not labeled examples? And there's three possible routes to addressing this, so kind of enhancing data efficiency. One is the machine learning approach of doing data augmentation. And that has some connection to some really interesting topics in mathematics, because now think about doing data augmentation of PD solutions. What does that mean, right? In which ways could you transform the input to a PD so that you know how the output of the PD is transformed as well, and you can use this mechanism to perform data augmentation. Like, if you give me a single example of input-output, so an input goes into the PD, generates an output, what kind of transformations can I come up with that I can use to, let's say, I can rotate my input, and then I know exactly how the output changes. So I can use that mechanism to do data augmentation. That takes us to the realm of Lie groups and symmetry transformations for PDs. And there's a very nice paper, actually, by my colleagues at Microsoft that exploit this for data augmentation specifically for PD neural surrogates. It's a really interesting topic. Then the more principled way for data efficiency is what I call inductive bias, which basically tells you, let's be more careful about how we design architectures in the first place and try to build in the architectures implicitly as much structure or constraints as we can. So if we know that a certain operator has certain symmetry properties, we can think about building equivariant layers. So there's a whole game there of how you can build architectures that implicitly bake in certain structure. Not the most straightforward thing to do, though. And then there's the easy way out. That's where I have most of my experience on, which is on using soft constraints during training. So don't touch the architecture. Just add more loss functions and penalty terms in your training, and try it in a soft way to kind of impose any prior knowledge that you have. And I think Matthias earlier talked about physics and neural networks. That's sort of like the space there. And this is what I would call self-supervised learning, in the sense that you don't really have, and you don't need labeled examples. You just need, let's say, the PDE constraint as a signal for training your model. So let me focus on the soft constraints, because this is the area that I know most about. And forget about the sketch on the top left. It's from a different talk, but this is your encoder, decoder, neural operator. My encoder here is something like a wavelet type of projection, and the decoder is an MLP. I haven't talked yet about nonlinear decoders, but we'll do that later on. But anyways, this is a neural operator that I came up with. And if you were to train this neural operator in a data-driven setting, you will just sample a bunch of functions from your input data set, you feed it through your operator, you get predictions, you compare those predictions against the target functions, and you take a mean squared error. So basically your training function is an empirical sample-based approximation of this expectation, right? Now, if you knew that your target output functions should satisfy a PDE that you know a priori, then what you can do is you can use automatic differentiation, take your neural operator outputs, compute all sort of derivatives that you need with respect to time coordinates, space coordinates. So the key point here is that those target output functions can be queried anywhere in space and time. But the query point is an argument of our architecture. So therefore, I can differentiate with respect to that query point, right? And I can compute all those derivatives with automatic differentiation, very much like you do in PINs. So this is kind of PINs, but with a neural operator architecture. But the same thing applies. And now if I can compute these derivatives, I can evaluate the residual of the PD. So if n is my neural, my differential equation, my operator that I know, and I know that my output function should satisfy this differential equation, I can compute the residual of this equation and introduce additional loss functions, maybe with some weights and some penalty parameters, to enforce a small residual during training, and maybe also to apply any boundary conditions that need to be satisfied. Okay? So that's the sort of PINs, basically, but for neural operators. Okay, questions on that? Yeah.
What about the choice for the microparameters? Is there any heuristic or?
For now, let's say you will suffer and then do trial and error. There are heuristics, but that takes us to a slightly different direction. I'll come back to that in a little bit. But let's say for now, you try, things don't work, you set lambda r to be 100 and lambda b to be 10, and then things get better. We'll come back to that because that's not a good answer. All right, so that setting now kind of defines two different learning problems. Okay, so let me just review them. The first one is the standard supervised learning that I started from, right? In the supervised setting, you have pairs of input and output functions, and you don't need any additional, you just use this loss function, right? And you can train a neural operator using those pairs. No problem there. The second type of learning problem is what I call the semi-supervised training, meaning that you have some pairs of input and output functions, but not a lot, and you have the PD constraint. And I think this is the setting where most practical applications live in. And this is the setting where I guess there is some promise of making those tools work for kind of more realistic applications. So there in this case, you would have, in this semi-supervised case, you can try to explain what this box means. Let's say this is the domain of your target output function. Now in the semi-supervised case, that means you have some measurements of those output functions. You do have some measurements. These are the red points. And in addition to those measurements, you can also enforce the PD residual to be small in the gray points. These are the collocation points for minimizing the PD residual. And this semi-supervised setting, you could also think of even splitting it into two parts. Maybe you can train a data-driven neural operator only on the pairs of input and outputs, which are little, so likely you will get a terrible model that overfits. So let's call that pre-training phase. And then you can fine-tune this only on the PD residual constraint. So that is more like if you want to split things into two steps. Or you can try to train the whole thing end-to-end using this entire function of fitting both the data and the PD residual, but then going through the suffering of tweaking those parameters or coming up with a way of adjusting the weights, the lambda r and lambda b. And finally, there is this more exotic regime, which I call self-supervised training. This is basically the PINS regime, where we have no information, no measurements of the output functions at all. So there's no measurements for these target output functions. The only thing we know is the PD itself. And for a well-posed problem, we also know the boundary conditions, right, for the problem to make sense. So the only kind of measurements we have for the output functions live at the boundaries of the domain, these blue points. And in addition to that, we have collocation points for the residual. So this is sort of like the purely PINS setting, what I call self-supervised, that you only have boundary data plus the PD residual. So yeah, in this setting, you do not need to run a PD solver to generate a training data set. The only thing you need to know is the distribution of your input functions, the PD form itself, and the boundary conditions. And then hope you can make PINS to work, or like this neural operator version of PINS to work. So now, going to that. Okay, here's an example. I'm going to quickly go through this example. It's from like a paper we wrote like 2 years ago. This example is just to show that, yeah, we can actually do that. We can use PD constraints for training DeepONets in this instance. If we do that, they become more data efficient, they become more accurate than plain DeepONets. Okay, no surprise there. Now, the disclaimer I want to make here is that when you go to this PINS setting that is fully self-supervised, you have to face some fundamental and unique challenges compared to the classical fully supervised case. So this is where really kind of expertise in PINS and deep learning and neural nets really comes handy. You cannot really expect things to work out of the box. So here's some issues that PINS suffer from, and as a consequence, this type of models will also suffer from. First of all, in PINS, and same thing in this setting of neural operators, we don't have any measurements for the output functions we're trying to approximate, right? And therefore, that makes really hard, our life hard, in terms of how we're going to initialize the architecture. Because with standard neural nets, you have a training data set, inputs and outputs. You normalize them, and then you do something like a Gloraux scheme to initialize the weights, right? And we know that this is really important. People did not know how to train deep neural nets before 2010 because they couldn't figure out that initialization. So it was like a pivotal moment in the history of neural nets when people say, hey, you have to be careful about how you initialize the weights. And to do that, you have to normalize your input and your output data to have zero mean and unit variance. Here we don't have output data, we don't know how to normalize, and therefore this whole business about how you initialize the weights goes out of the window, right? So typically when you're working with pins, you start from a really, really crappy initialization. There's no way around it. And then you hope that your optimization and the way you set up the problem will eventually converge where you want. But that where you want point could be really, really far away from your initialization. So that's a whole open area of coming up with good initialization. So if I know the PDE, what is a good initialization for my neural net? That's an unanswered question. All right, problem number one. Problem number two, we have now these multiple loss terms that could compete against each other, could have different magnitudes, and the loss landscape could become really, really stiff. So, there are certain directions that our network parameters are very sensitive, or sorry, the predictions are sensitive with respect to the network parameters, and other directions that are not. And then just saying I'm going to use the Adam optimizer could be a poor choice. Like this whole optimization problem of pins is a problem on its own. You have multiple objectives and constraints. And then the final issue is that PD solutions often sometimes could have low regularity, or could have a broadband frequency spectrum with low and high frequencies interacting. And if you were to use a plain MLP as your decoder, you may suffer from something called spectral bias. So MLP architecture have this tendency of approximating smooth low frequency functions. And if your target function has a lot of variability, an MLP will have very slow convergence. But for that, more or less, there are some tricks where you can use things like Fourier features or positional encodings and other tricks to kind of mitigate the spectral bias issue. So these are some of the problems that the fully physics-informed setting will suffer from. So yeah, going back to the question, yes, you can do that, but good luck doing that in some sense. I have this super busy slide. This is just like a whole bunch of things we've done with my group, like in different kind of address different aspects of all those issues, and still those issues are not addressed. These are just some ideas that improve things. And have allowed us to look at more interesting problems, like in fluid mechanics or more chaotic type of PDs, like the Kuramoto-Shevasinsky equation. I'm not going to go through the details here. There's references. We can talk about it later. But the message here is that it's not going to work out of the box. You can't simply just throw whatever choices work for computer vision. You have to kind of revisit a lot of fundamental assumptions and get a better understanding. So there's a need for more effective architectures and training algorithms specifically for this pin setting that lives in its own corner of deep learning that is a little far from what works in computer vision in other domains. So we are still at the very early stages. Like, a lot of people go out and say, hey, pins will solves everything. Probably not, right? There's still a lot of work to be done. That is not to say that the method is bad. It's more like that we don't know how to properly use neural nets in this setting. Okay. Of course, neural nets are also bad when it comes to accuracy, right? So if I want to deal with chaotic systems like this Kuramoto-Shevasinsky example, I need to have really high accuracy. Otherwise, in finite time, those errors I'm committing are going to make the trajectory diverge. So that's another issue that I think neural networks are not well suited fundamentally to model PDE solutions that have a chaotic behavior because of these accuracy issues. All right. With that in mind, some shameful advertisement. We have this new pins library online based in JAX, and it's accompanied by a paper that we put out about a month ago, and we call it an expert guide to pins. It's not related with neural operators, and this library does not have any neural operator functionality. But in this paper, we kind of outline a lot of tricks that help in terms of making pins work, and we kind of outline a lot of the practical issues that users might have to deal with. We show some diagnostics for identifying issues, and then we also have a lot of examples. So let me see if I can find this, just to walk you through the library itself. So yeah, the goal of this library in this paper was basically two things. One, to give a guide to new users to kind of understand some basic best practices. The second goal was to integrate things that we have learned over the last 2-3 years from different papers and have them in one place and have basically a guide or a cookbook of how one can use those different tricks. And the third one is to put forth some really state-of-the-art results for benchmarks for which we know that pins don't work. So yeah, for me and I think for others, it's usually very frustrating. There's like many pins papers written now on a very regular basis. And they all say, hey, we do better than this 2017 Rice et al. Thing. Oh, okay. Okay, great. But basically, that's an extremely weak baseline. So the other, one of the key messages in this paper, we have this collection of examples that you can see here. There is many different fluid flow examples, liquid cavity, flow of a cylinder, Cronus-Lasinsky equation, Darcy flows, Euler equations, blah, blah, blah. And for each one of those, we have extensive ablation studies, testing all those different options in neural network setup. You use Fourier features, you don't use. You normalize the gradients, you don't, the different schemes for selecting those penalty parameters, the weights in the loss function, and so forth. So we have a very extensive collection of those, and also for each one of those, we report the results. And basically, we also have the state-of-the-art result that we wish anyone who uses this benchmark in the future, that's the result that you should be comparing against instead of the outdated stuff. That's basically what the paper is about. And then finally, the library is written in a way that really researchers can use it. It's not a practitioner's tool. There's no crazy documentation. But if you understand your neural nets and you know a few things about pins, the framework is written in a way that can really enable you to do research and further develop tools in the pin space. So yeah, I was not planning to present this today, but since you can push me in that direction, yeah, you can feel free to play with it and send us a comment and read the paper and so forth. All right, so 2-3 more minutes. Anything else? This whole lecture was on FNOs, but we kind of departed, which is a really good model. So you should use FNOs as a baseline. Although in the next 2 lectures, I will also show you cases where FNOs kind of suck. Okay. And in fact, if you want a really strong baseline for this kind of operator learning regression task, probably use UNets, computer vision tools, discretize first as a baseline. Of course, yeah, there's this argument that the UNet is not a neural operator in the sense that you cannot evaluate it anywhere. Well, you can always do interpolation, but it gives you a very strong baseline to start with. All right, maybe we can wrap it up and we continue. Let's see. Am I right here? Sorry, no. Oh, I messed it up. I'm over time. Okay, sorry.